You can see how I solve them. But you can subscribe to our YouTube page. Alrighty, it's about to be 6:10, so I'm going to officially begin. All right, welcome everyone. Welcome to our mock final exam review for Math 175. Our review is being presented by the MS3 Censor. That is Raphael, our director. The assistant director is me. My name is Anthony. I know some of you that comes to the Math Censor. Some of you I probably never met, or I probably saw you by face. That's cool. So anyways, I'm gonna go through this mock exam. If you have any questions as I go through them, please let me know. What I'll do is I'll pause, at least a 1 minute pause, where you can take a screenshot of the problems if you need to. Okay. All right. So here's problem number one. Problem number one states compute the derivative dm dx, right? Take the derivative of m with respect to x for our function m equals x to the fifth over 8 plus 19e to the 2x minus 3 square root of pi. So, how would I find my derivative of this equation?
Was that a question?
Yeah, that's a question. How would you find this derivative? What do you do?
So you would have to basically take the derivative of each individual component and
That's
then
right.
combine them.
Yeah, that's right. You take the derivative of each individual term, and then you do some sort of simplifying at the end if needed, right? So again, when you're finding this notation, the derivative of m with respect to x, that is equivalent to just saying m prime, right? So we take the derivative of each term. All right, let's start with the x to the fifth over 8. What is the derivative of x to the fifth over 8? Anybody? Miss Chin, you got to be careful. In the chat, you put 5 over 8x to the fourth. Got to be careful with the way you type it out. There you go. Now I kind of get what you're saying there. Yes, it's 5 over 8 times x to the fourth. Yes, thank you, Shirley. So another way of just saying your derivative x to the fifth over 8, you could just take the derivative of the numerator because it contains the variable. Your denominator is a constant, so you can leave it alone. So you can say that the derivative of that numerator is 5x to the fourth over 8. Okay. Okay, that's the first term. What is the derivative of 19e to the 2x? First of all, what derivative rule is needed in order to take the derivative of 19e to the power of 2x? The chain rule, that's right. Thank you, Nora. So, just recall for the exponential function e, if you take the derivative with respect to x of e to the u, where u is a function of x, then this derivative, the formula states that, again, the derivative with respect to x of e to the u will be what? Careful, Miss Chen. It's e to the u, but you're missing something.
-1.
No, no -1 here. Not with the exponential. There you go. It's e to the u times u prime. Okay, so if I wanted to find my derivative with respect to x of 19 e to the 2x, then by the chain rule, what would be my u?
2x.
2x. So we're going to have the original function, 19 e to the 2x, times the derivative of 2x. So what is the derivative of 2x? Is 2.
2.
And now you can combine this. 19 times 2 is what?
38.
38. So you get 38 e to the power of 2x. So derivative of 19 e to the 2x would be 38 e to the power of 2x. And then lastly, the derivative of -3 times the square root of pi. What would be the derivative of -3 times square root of pi? Yeah, that's right, Miss Chin. It's going to be 0 because the derivative of any constant is always 0. So you could just include it, say that, hey, the derivative is -0, so that way your professor can see that, you take the derivative of a constant correctly. And now you just briefly simplify it, right? Just removing the -0. So this final answer should be 5x to the 4th over 8 plus 38 e to the power of 2x. Now, I did show you the chain rule here for exponentials, namely e to the u. But in addition to that, let's just say I wanted to just find the derivative of 19 e to the x. Do anybody know what the derivative of let's just say e to the x will be?
It's e to the x.
Yeah, the derivative of e to the x will always be itself. So if I ask you to find the derivative of 19 e to the x, it's going to be 19 e to the x, right? It's going to be that constant times e to the x. Any questions here for me?
And then the 3 square root of pi, they're both constants, right? So that's why it's 0.
That's right. The derivative of any constant, let's call C our constant. The derivative of your constant is 0. Okay, so 3 square root pi or -3 square root of pi is your C. So the derivative of that constant is 0.
I have a question.
Go for it.
So every time we have an e, is always going to be the derivative of e times the original number in the front?
Well, if it's 19 e to the x, then yes. I mean, if you have a constant times e to the x, then yes, it's constant. Derivative will be the constant times e to the x. But the way that you said it was this. If I were to do, I'll put it over here in this bubbly. Let's say if I had the derivative now of 5e, what would the derivative of 5e be?
Wouldn't it just be 5?
No. In this notation, nope, not true, Miss Shirley. Got to be careful with this example here. There's a difference between the 19e to the x and the 5e here. The most obvious is one of them has the number 19, one has the number 5. But
would it be 0?
This one has to be 0. Why is it 0, Miss Torres?
Because it's a constant.
That's right.
It's no variable.
That's right. There's no variable there. Essentially, e is a number, right? So if you take a number and you multiply by 5, still a number. So the derivative of 5e is just 0, okay? Derivative of 19e to the x is 19e to the x. And if I had 19e to the 2x over here on the bottom left, then I had to apply a chain rule. So this problem here, I just, showing you the difference between e versus e to the x versus e raised to e raised to the power of u, where u is a function of x. Any questions?
So for the 19EX, it's 19EX because you take the EU, which will be 19EX, and then times the U to the first, which will be 1, right?
Not even. Technically speaking, what you're allowed to do with derivatives is that if you have a constant term, you can pull it out of the derivative, right? So the longer way of showing this is saying that you have 19 times the derivative of e to the x. You can pull the constant out. And if I do pull this constant out, then it's going to read as 19 times the derivative of e to the x. E to the x, its derivative is still e to the x. So when you put it back together, it gives you back 19e to the x.
I have a question.
Go ahead.
E to the power of 0, 1.
E to the power of 0?
Yeah.
Yeah.
So wouldn't we say that 5e is 5e to the power of 1?
Well, if you have 5e to the power of 1, e to the 1 is still a constant. Right? It's numerically like 2.71828, yada yada yada. So when you multiply by 5, you still got a constant.
Okay.
Yep. Any other questions? Okay, let's move on to problem number 2 now. Wait, Ms. Chin, you said if e to the power of x, e to the x, if x is equal 1, there will 0. Yeah, because it's a constant. It's still a number, so the derivative of a number is 0. It's still going to be 0.
However, e to the 0 is equal to 1, but that still equals to 0 because it's a constant.
That's right. That's right. That's right. Okay, let's look at problem number 2. It states compute the derivative h prime of x for when h of x is equal to 5x squared minus 8 divided by 3x squared minus 4. So, what derivative rule is used to help you compute h prime of x?
The quotient rule?
Yeah, that's right. You have to use a quotient. So usually when I solve this problem, or when I show my students to solve this problem, I write out the quotient rule, and then I tell them that we're going to do some scrap work, and from the scrap work, we're going to do their favorite part of a term paper, where most students like to copy and paste things that they read from the internet. So when I write out the quotient rule, the formula, we're going to do some scrap work on the side, and then we just copy and paste it into the formula and we simplify. All right, so the quotient rule states that if you take the derivative with respect to x of f over g, then this is equal to g times f prime minus f times g prime divided by g squared. Okay, so when you look at your function h of x, you should be able to identify your f and your g. F is typically the top function, g is the bottom function. So when I do my little scrap work here on the side, I list them, right? I list out my f, I list my g right next to it, and underneath I'm going to get their derivatives. So since I said f is the top function, you should be able to identify that it's going to be 5x squared minus 8, and g is going to be 3x squared minus 4. Right underneath, you write out your derivatives. Oops, made a little typo there. So, what is the derivative of 5x squared minus 8?
10x.
That's going to be 10x. And the derivative of g prime of x?
6x.
6x. So, the way that my scrapwork is designed is that it looks like we're doing some sort of informal cross multiplication. You take f times g prime, you take g times f prime, right? But just note that for the quotient rule, the g times f prime goes first. So when I copy and paste this into my formula, we're gonna our formula for the quotient rule, we get 3x squared minus 4 times 10x minus, in parentheses, 5x squared minus 8 times 6x. All of that gets divided now by our bottom function squared. Yeah, Carlos, that's a good way to remember it. Low D high, high D low. So g squared is 3x squared minus 4. So 3x squared minus 4 squared. All right. All you got to do now with your quotient rule is just simplify the top. The bottom you typically leave alone. So in the numerator, I can now take the 3x squared and the negative 4, multiply it by negative 10x, or sorry, 10x. So 3x squared times 10x will be 30x cubed. Negative 4 times 10x is negative 40x. And now I have to do the same thing to the negative 5x squared minus 8 times 6x, right? So just be mindful that because there's that minus sign outside of the 5x squared minus 8, you technically can distribute that inside your parentheses, which will basically change the signs of each of those terms. In addition, you can also take the 6x and multiply it by whatever's inside that parentheses. Okay, so here's how this works. If I take the negative on the outside, and I multiply it by the 5x squared, then the 5x squared becomes negative. That would read as negative 5x squared. Now, if I take negative 5x squared and I multiply it by 6x, then what is negative 5x squared times 6x?
It will be negative 30x to the third power.
That's right. You get negative 30x to the third power. And then you take the negative again and you repeat the process. This time, it's negative times negative 8. So negative times the negative 8 would be what?
Positive 8.
Positive 8. And then positive 8 times the 6x is? $48x. Yep, you got it. 48x. And you divide this now by your denominator, which is 3x squared minus 4 squared. Okay. So you simplify this. You just got to combine like terms in the numerator. So 30x cubed. If I combined it with the negative 30x cubed, then that would be what?
It will
0?
cancel out.
That's right. That will cancel out. Then you have negative 40x plus 48x. That would be, careful, Omar, I can't say 8. 8x. There you go, you fixed it. So you get 8x, and then your denominator, you just leave it alone. 3x squared minus 4 squared. And that will be h prime of x. Any questions?
I have a question.
Go ahead.
When are you able to take the denominator of the quotient rule and multiply it by the numerator in any other like in an instance where you can do that to like solve for x or something?
I think you would do that if you're looking at fully simplifying a derivative that involves a quotient rule. Like for example, if you have trigonometric functions and you can see that somehow in the denominator you got I don't know, I'm just going to make an example up. Let's just say quickly that the denominator is cosine squared x, right? But the numerator is sine squared of x. And let's say that was a derivative of some quotient. I don't know what was the original problem. Again, just making something up here. This you can simplify, right? Anybody remember what sine over cosine is from trigonometry? No, not cosecant. Sine over cosine. Not secant. Tangent. There you go, Miss Chin. So sine over cosine is tangent. So this is like a case where, this is just a side stuff here. If I found that my denominator was cosine squared of x, and somehow my numerator was sine squared of x after I applied the derivative, the quotient rule, I simplified the numerator somehow. This is a case where I could simplify it, if I had, a case where it was like, here's another aside. Put another bubble here. Let's say if I had e to the x over e to the 2x, then this is something that I could simplify. If I do, it will be 1 over e to the x. Okay? I don't think you have to worry much about simplifying that denominator. When the derivative rules, namely the quotient rule, was first introduced to you, typically we will say leave the denominator alone. Just worry about the numerator, but you can leave the denominator alone.
I have a question.
Go ahead.
So let's say like once we're practicing there doing the final, can we like, there's always going to be two values that cancel out, right?
I don't know. I can't tell you. It depends on the problem. It depends on the scenario. Like if the variables weren't like you see, if you had 5, like you see the numerator and denominator have both the same degree. They both raise both to powers of 2. If one is raised to the power of x and the other is raised to the power of x squared, then it's a possibility where nothing will get canceled. There's many different factors as to why something can't get canceled out here. I could give you a trinomial on the top and a binomial on the bottom, and then good luck.
So the -8 times 6, it's a positive 48 because of minus sign for the first minus sign, right?
What I'll do is I'll change the color scheme of those arrows. What I was trying to say.
Can you explain that part again?
Yeah, so what I did was I distribute the negative sign inside the parentheses, and then simultaneously I was multiplying it by the 6x, right? So like for example, if I were to change, if I multiply the negative 5, the 5x squared by the negative sign on the outside, it becomes negative 5x squared. But when I multiply by 6x now, it becomes negative 30x cubed. Similarly, negative of -8, 2 negatives make a positive, that gives you positive 8. So positive 8 times 6x is 48x. Sounds good, Ms. Torres?
Yeah.
I'll tell you this much. So far, the turnout was it's pretty large turnout. I wasn't expecting 25 people here so far. Pretty good. It's larger than the number of students that I teach during the semester all year. Yeah, I know. Omar, I feel like you were once my
So
student.
are you also a professor?
That's right, I am. Well,
Because
well, I'm an adjunct lecturer, but that's my correct title. But I'm the assistant director of the math.
the professor that I have, he doesn't let us ask questions, nothing. He doesn't really teach us nothing. We basically have to teach ourselves. So, and a lot of people are agreeing with me.
I got
Even
you.
like at the midterm review, he was not like letting us ask questions or nothing.
Maybe he wasn't in a good mood that day. Probably something is bothering him personally. Yeah, Omar, your name did sound familiar. Somebody else said they were in my class. Who else? I think Miss Chin was.
Good professor.
Yep. Yeah, Miss Chin was in my 108. Mm-hmm. You know what's crazy, Omar? I remember your name, but I just don't remember your face. I'm sorry. Yeah. It gets harder. That's true. All right. Let me continue before I sidetrack. That can happen often. Here's problem 3 now. Problem 3 states, write down the equation of the tangent line to where the graph of y equals 3 plus 4 ln of 2x minus 1 at the point where x is equal to 1. This problem, when you're writing the equation of the tangent line, you typically do this in 4 steps. What is the very first step when you have to find the equation of the tangent line?
Don't we have to find the value for y?
You could do that. I do that later on. But there's something else that I get out of the way right away. I'll give you a hint. What class are you taking? You're in Calculus 1. What is one topic that you learned the most about Calculus 1?
Find the derivatives first?
That's right. You find your derivative, right? Worst case scenario, if you're ever stuck on any problem, and, namely from problems, let's say 1 through 14 on this final, if you're stuck on any problem, I think the only ones that you got to work, that you probably, this excludes are from 1 through 14 are the limit problems. But any other problem like that, worst case scenario, very first thing you do is find your derivative. So that's our step 1, finding y prime. So what is the derivative of 3?
0 is a constant.
Yeah, derivative of 3 is 0. That's your constant. Now, how do I find the derivative of 4 ln of 2x minus 1? Namely, the ln of 2x minus 1. What derivative rule is required here?
The product rule?
Not a product.
That's a chain rule.
That's a chain rule, right? So, let's just make some notes here. If I were just to give you ln of x, right, I ask you to find the derivative of ln of x. Anybody know what's just the derivative of ln of x?
1 over x.
There you go, Carlos. It's 1 over x. But if I ask you to find the derivative of ln of u, where u is a function of x, it's a chain rule. Okay, it's a chain rule. What is the derivative of, well, what does the chain rule state regarding ln of u when you take its derivative? There you go. Yes, so either notation is fine. I typically just say u prime over u, right? So when I look at it as a fraction, the denominator is the expression inside of the natural logarithm, right? That's going to be your u. It goes on the bottom, and on the top you have your derivative. Okay, so because I have 4 ln of 2x minus 1, then I know that in my derivative, the 4 is the constant multiple. It will come down for the ride. So I'm going to say 4 times, in parentheses, we're going to have u prime over u. So if my u is 2x minus 1, then what is u prime? Mm-hmm.
So
That's right. It's 2. So you put it together, you got the derivative on top, 2, and on the bottom, it's 2x minus 1. Okay, so just to clean up our derivative a little bit, the 0 goes away. Now, when you have 4 times 2 over 2x minus 1, you can rewrite this as 8 over 2x minus 1. Right? 4 times 2 is 8, so you divide that by 2x minus 1. So that's your y prime. Now, there's another reason why the very first step it says, hey, get your derivative. Because what am I allowed to do once I have my derivative? What can I actually find with this derivative?
can you plug in x now to find y?
I do that in step 3. There's something that comes before that, actually. And it comes directly after I find my derivative. Once I have my derivative, I can plug x into it. But when I do plug my value of x into this derivative, what am I actually finding? A slope. That's right, Francisco. You're finding a slope. That slope is namely the slope of the tangent line. So the way, what letter, by the way, do we use for slope? M. Okay, good. You guys learned something from Math 171, Omar. M stands for slope, right? So we're finding the slope of a tangent line. So we say M tangent, M10. Okay, M10. So you get M10 is equal to y prime at x equals 1. Okay, y prime at x equals 1. So it means that you're just evaluating your derivative at x equals 1 to get your slope of your tangent line. So what's 2 times 1 divided by 1? Minus 1. Let's take care of that bottom. 2 times 1 minus 1. That's going to be 1. Yeah, 2 times 1 is 1. 2 minus 1 is 1. So 8 over 1 is just 8. There you go, Carlos. That's your slope of your tangent line. All right, now that you got your slope of your tangent line, you can go ahead and find y. The way that I denote y is I call it y1. Okay, so y1 is just equal to, again, that's where you plug in the value of x into the original equation. So it's 3 plus 4 times ln of 2 times 1 minus 1. All right, so let's work out inside the parentheses. I know that 2 times 1 minus 1 is 1 from previous results there above. So we get 3 plus 4 ln of 1. Alrighty, what's ln of 1? That's right, ln of 1 is 0. So if ln of 1 is 0, what's 0 times 4? 0, right? So we're going to get 3 plus essentially 4 times 0, which is still 0. So your answer here is 3, right? Whenever x is now equal to 1, that means y1 is 3. All right, so we got the first 3 steps done. The fourth step now is where you write out the equation of your tangent line. You can begin with point slope form and then convert it to slope intercept form. So anybody remember what point slope form looks like?
Y minus y1 equals slope.
So I'll call the slope M10 here.
Then parentheses x minus x1.
Yeah, so x1 here is going to be precisely the value of 1, right, to avoid any confusion here. So when we plug things in, we get y minus 3 equals 8 times x minus 1. And then I do a little bit of rewrite. So first, I can distribute the 8 inside the parentheses. This gives me y minus 3 equals 8x minus 8. And then I add 3 to both sides of the equation, so that way I can write the equation in slope-intercept form. So this will give us y equals 8x minus 5. Any questions?
Yeah, I have a question.
Go ahead.
So the reason I was kept mentioning that we have to plug in X is because I usually do that first. Would it change the way, especially with the ln and the y, would it change the way I get my answer?
No, it shouldn't at all.
Okay, yeah, because I usually do plug in. I usually find y first, then I find the slope. So it really doesn't matter, right?
Well, before you get to the slope, you would have to find your derivative, right?
Oh no, I meant like once I find the derivative, I plug in the x value to find y first, and after I get the y, then I get my slope. That it wouldn't matter.
No, it wouldn't matter as long as you plug it into the correct functions, right? Like you plug in x into the original equation to get y or y1, and then you plug in 1 again, but this time into your derivative to get your slope.
ln1 is the same thing as log e to the of 1, right?
Log e with a log base e of yes.
Log base e of 1, right?
Mm-hmm.
Which e1 is 0. Okay.
Well, e to the 0 is 1.
Yeah.
Yeah, there you go. That's true. That is true.
So in problems like this, first we find the derivative, then we find the slope, and then we plug in for y for y1.
You plug in x for y1, yes, into the original function.
Yeah, that's what I meant. Yeah.
Okay.
Okay.
And then the last step is the pre-calc step of writing the equation of the tangent line. You first start with the point slope form and then convert it to slope intercept.
Okay.
Anybody else? Any questions? Okay, let's go on to problem number 4. So problem number 4 states, determine the slope of a tangent line to the graph of the equation 4x cubed plus y cubed plus 3xy equals 40 at the point 1, 3. So in this example, first of all, when I'm finding my derivative here, is the derivative with respect to what variable? Does anybody remember?
Respect to x?
Respect to x. That's right. You have to take the derivative with respect to x. In particular, what method are you using here when you're finding your derivative? The big shotgun of the methods. Implicit. There you go. So problem number 4 is an example of implicit differentiation, where we're taking the derivative of every single term in this equation by x, right? So to start it off, you say d dx. That's the notation implying that you're taking a derivative of the entire equation. So it's 4x cubed plus y cubed plus 3xy is equal to 40. All right, so walk me through this. What is the derivative of 4x cubed?
12x.
Can't just say 12. It's 12 what?
X.
To the power
X
of x. Yes, x squared. There you go. 12x squared. Now, what is the derivative of y cubed with respect to x?
It will be 3y squared times dy dx.
There you go. So some instructors, they use y prime here. I use dy dx because sometimes for me, I confuse y prime with y to the first when I'm doing something that involves a lot of algebra. So I'd stick with the dy dx notation. Okay, good. Now, if I want the derivative of 3xy, what derivative rule is required there?
The product rule.
Mm-hmm. It's a product. So just another recall moment here. If I want to find the derivative with respect to x of f times g, this is the same thing as saying f times g prime plus g times f prime. So I could do a little bit of scrap work here, and then I'll copy and paste it back into this equation. So I'm going to define this as scrap. I got to write a little smaller here because I don't know how much more space I need. But let's say f is the 3x, and let's say that my g is y. What is the derivative of 3x?
3.
3. And my derivative of g, if g is equal to y, then g prime should be?
dy dx.
Very good. So when you put this together, you take 3x times dy dx, and then you take y times 3, or 3 times y. Right? It's like when you have your scrap work set up appropriately, it looks like a cross multiplication. Right? So it's 3x times dy dx. Then the derivative of f times g, or g times f prime, that's going to be 3y. And lastly, the derivative of 40.
0.
0. Okay, good. I'll tell you what. That was the calculus step. After this is just a bunch of algebra and arithmetic. Okay? Because when you want to find the slope of your tangent line, remember dy dx is your notation for derivative, right? So you have to now isolate dy dx. You got to get it by itself, and once you do, you're able to plug things in. So with all that being said, the terms that do not contain a dy dx, you can move it to the other side of the equation. For example, you can subtract 12x squared and 3y on both sides, right? So I'm subtracting 12x squared and 3y on both sides. The 12x squares would have canceled out. The 3y's here would have canceled out. So this would give us 3y squared dy dx plus 3x dy dx is equal to negative 12x squared minus 3y. Now, when you have the terms that contain only a dy dx by itself on one side of the equation, just like how this left-hand side of the equation looks like, then you can factor the dy dx out of it. If you do so, then inside the parentheses, you will have 3y squared plus 3x, again, is equal to the right-hand side of this equation. And now the last thing to do here is to divide everything by 3y squared plus 3x. So what we're going to have is dy dx, right on the bottom, is equal to negative 12x squared minus 3y over 3y squared plus 3x. Since I have my derivative, I can now find the slope of the tangent line, right? So we say that m tangent is equal to dy dx at, or being evaluated at, the given order pair, 1, 3. So wherever I see an x, I replace it with the number 1. Wherever I see the variable y, I replace it with the number 3. This will give us negative 12 times 1 squared minus 3 times 3 over 3 times 3 squared plus 3 times 1. Okay, so if I work this out, in the numerator, you will get something like -21, I believe, right? Because 1 squared times -12 is still -12. -3 times 3 is -21. And then on the bottom, 3 squared is 9, so 9 times 3 is 27. 3 times 1 is 3, so 27 plus 3 is 30. And you could have reduced your slope if you wanted to. If you reduce this, what would the final answer be?
-7/10.
Yeah. So you have -21/30, or you can say -7/10. Okay.
I have a question.
Yep, go ahead.
For the final answer, so -7/10, can we write m equals -7/10?
Yeah, you could say M10 equals -7/10.
I have a
Anybody?
question.
Go ahead, Ms. Torres.
So I lost you like in the middle where you added the -12x squared and then the -3y, -12x squared, -3y. Like, where did that come from?
Well, the idea here, the goal is once you take the derivative with respect to x, you want to isolate dy dx by itself. So the reason why I subtract the 12x squared and the 3y on both sides of the equation.
Oh, so to get it by itself, you have to do it to one side and then to the other side. Okay, I get it.
That's right. One side of the equation should have the dy dx terms, whereas the other side of the equation does not have the dy dx terms. This allowed me, if you look at where I crossed out the 3y squared plus 3x, this right before that, this allows me to factor out the dy dx, and then whatever was remaining inside the parentheses, I divided both sides of the equation by, again, whatever's remaining inside the parentheses. All right. Anybody else? Any questions? Okay. I'm going to move on to problem number 5. So in problem 5, it states that we have to compute the derivative of dp dz for the function. Oops, there's a typo there. There shouldn't be the derivative sign there. Oopsie. We're finding the derivative of the function p of z equals 100z plus z times cosine of z raised to the 5th power. So essentially, how can I find my derivative? Or how can I find, right? We're trying to find.
This is a power rule.
Careful.
You're gonna say, yeah.
You just
No,
can't say
no
a power rule here.
We have to use the chain rule.
It's a chain rule.
Oh,
right?
chain rule. I'm sorry.
It's okay. You're not wrong by saying the power rule, because you're using the idea of the general
Of the power.
rule.
Oh yeah.
Yep, you're using basically a general power rule here. But keep in mind that you do have to take the derivative of the inner function. So here's my crazy setup for finding when I'm dealing with a chain rule of such nature, namely when I have the general power rule. Usually I let u be the inner function, right? I make a U-substitution. So in this problem, what should be my u? What can we consider to be our inner function?
100z plus z cosine z.
That's right. That's right. you get 100z plus z times cosine of z. Oh, wow, now I remember who Nora is. I'm sorry, Nora, now I remember who you
Oh,
are.
it's okay.
It's all right. Okay, so we let u be 100z plus z times cosine of z. And now what I'm going to do is rewrite, you see, the function p, by the way, was in terms of z. What I'm going to do is rewrite it in terms of u. So if we let u be 100z plus z cosine of z, then p of u should be, well, everything that was inside of the parentheses is getting replaced by u. So the only thing that remained from the original function was the power of 5. So you have u to the 5th. Okay. Now the way that the chain rule works is that I'm going to take the derivative of u in terms of z. I'm going to take the derivative of p of u in terms of u. And then I just got to multiply them together and do a little bit of rewrite at the end. So let me take care of the easier derivative first. If p of u is u to the 5th, then when I take the derivative of this function in terms of u, then it's going to be what?
5u to the 4th power.
That's right. You're going to get 5u to the 4th power. Now, since we let u be 100z plus z cosine of z, then I have to find u prime. But be in mind, or keep in mind, that u prime means that you're finding the derivative of u with respect to z. So what is the derivative of 100z?
Good.
Yeah, that's going to be 100. The derivative of z cosine of z, that's going to be what?
It's gonna be product rule.
That's right. It's a product rule. It's a product rule. You would have to, because again, how do I know it's a product rule? Well, what operation separates z from cosine? It's a multiplication, right? So we could do a little bit of scrap again. Let's make f be z and make g be cosine of z. So f prime is going to be, well, what's the derivative of z?
0 is a constant.
Ooh, careful. That's a z. Z for like
It's 1.
zebra. Yeah, it's going
1.
to be 1. That's right. So the derivative of z, my bad, it probably looked like a 7 to you. My bad. The derivative of z is 1. Now, what is g prime going to be? There you go.
Minus sign.
Minus sine of z.
Z.
All right. So by your product rule, you would just, again, multiply these two things out, like cross multiplication, f times g prime, g times f prime. So if we take f times g prime, z times negative sine of z, informally, you could just take the negative and stick it in front of the z there. So it becomes minus sine, oops, my bad, minus z sine of z. And then your derivative of f was 1 again, so 1 times cosine of z is just going to be cosine of z. So that's plus cosine of z. All right, now that I have my p prime of u and my u prime, essentially I have my derivative of the outer function. That's the 5u to the 4th. The derivative of your inner function is specifically u prime, the 100 minus z sine of z plus cosine of z. So, again, when you just multiply those two things out, p prime of z is going to be 5u to the 4th. And then in parentheses, you write out your derivative, 100 minus z sine of z plus cosine of z. But one last thing to note here is that everything has to be written in terms of z. So because we originally let u be 100z plus z cosine of z, then this is going to be 5 in parentheses, 100z plus z cosine of z raised to the 4th power. And then, again, you just write out your u prime. That's the 100 minus z times sine of z plus cosine of z. Okay, and that'll be it. That'll be your answer. Any questions? All right. We'll continue going on forward. Or does everyone have it copied down? They took a picture. Good. No questions. Usually when it's silent like this, I worried.
Can you give me like 5 more seconds to
Sure.
copy? Thank you. Okay, you could go ahead.
Alrighty, sounds good. So let's look at problem 6. It states that we want to compute the following limit. So it states that the limit as theta approaches 0 of -5 sine of 4 theta times cosine of 8 theta divided by 3 theta here. Okay, so when you were learning about limits, there was one special limit that you learned earlier on regarding trig, right? What was that special limit? There was a special limit that you've learned earlier on in the semester.
To infinity?
No.
No. Oh, with the limit approach from to the for the number from the left and right.
Not for this case.
Oh,
There you go, Miss Chin. You have sine of x over x is equal to 1. However, I just can't write this statement. I have to write a limit statement. It's the limit as x is approaching what number that makes sine of x over x 1? Yeah, x is approaching 0. Limit as x approaches 0 of sine of x over x is 1. So essentially, when I'm going to rewrite my limit here, I'm basically going to, instead of having this this limit written as a single expression, I'm going to split things up here. And in particular, when I split things up towards one of the latter or later steps, I'm going to use my special limit here. So first of all, I mentioned this earlier about derivatives. If you have constants, you can typically pull them out, right? Like a constant multiple. So in this problem, you can do the same thing. Can anybody identify your constant multiple that you can remove from the limit?
-5.
The -5, and there's something else. The 3, that's right. So what you're gonna have is -5 over 3 removed times the limit as theta approaches 0 of, now here we got to be careful. You see, the way that you read this is sine of 4 theta times cosine of 8 theta divided by theta. That's what's remaining. So either the theta that's in the denominator divides into sine or cosine, but not both. It's one or the other. Since I have to use my special limit, theta has to divide into sine. So we say limit as theta approaches 0 of sine 4 theta over theta times the limit as theta approaches 0 of cosine 8 theta. Right? In other words, I'm basically deassembling this one limit problem into multiple parts. I remove the constant multiple. I rewrite the first limit as theta approaches 0 of sine 4 theta over theta, because, again, theta can only divide into sine or cosine, but since I know I need to use my special limit eventually, I'm going to divide it into sine, and then by the product rule for limits, you will say now times limit as theta approaches 0 of cosine 8 theta. Okay. Now, if I want to use my special limit to say that sine of x over x in that form goes to 1, then whatever's inside the parentheses must match with whatever's in the denominator. Inside my parentheses, I have a 4 theta, and in my denominator, I have a theta. They don't match, unfortunately. Algebraically, you can make them match, right? If I want to make basically a matching pair here, in my denominator, what should I place in front of the theta? A 4. Yeah, that's right. You place a 4. But this is a rational expression. It's a fraction. So whatever I do on the bottom, namely multiplying by 4, then I also have to do it in the numerator. I multiply both 4, top and bottom, okay? So this will give me 4 times, so I'll put this in a different color for us. So you can see that this was like a second step here. I get 4 times sine 4 theta, and then I multiply by 4 on the bottom, you get 4 theta. Okay. Now, the 4 that I use to multiply in the numerator, I really don't need him anymore. I just used him to sort of construct our special limit here. So this 4 is also a constant multiple that I can pull out. All right. When I do so, this will read as follows. Negative 5 thirds is going to be multiplied by a 4 eventually, times the limit as theta approaches 0 of sine 4 theta over 4 theta, times the limit as theta approaches 0 of cosine 8 theta. All right. So what is negative 5 thirds times 4?
Wait,
That's
can
right.
you repeat the question?
Oh yeah, I asked what's negative 5 thirds times 4, but I just
Oh.
looked at the chat. It says negative 20 over 3, so that's right. So you get negative 20 over 3. In the middle, the limit as theta approaches 0 sine 4 theta over 4 theta. That's all just a fancy way of saying now the number 1. Now the last one, you can use direct substitution here. All right, if I replace theta with 0, what's 8 times 0? 0. But cosine of 0, so put a little star here, cosine of 0 is equal to what? 1. That's right. So you get negative 20 over 3 times 1, which is?
Negative 20 over 3.
There you go. Negative 20 over 3. Final answer.
Question.
Go ahead. You can ask.
So the goal of this problem essentially is to separate all the constants until we have the sine x over x equation, which will give us 1.
Well, it was more than just separating. I did separate at the very beginning, but the reason for it is because once I'm able to separate things, it's easier to evaluate. So I knew that I needed to use my special limit eventually. So yes, by splitting it up, you were able to play around with it a little bit, play around with it algebraically, so that way, when you eventually get something like limit as theta approaches 0 of sine 4 theta over 4 theta, it's going to be 1.
I have a question.
So cos and a constant with theta is always equal to 1.
Wait, my bad. I missed your question. I'm sorry.
So you see how like up here you have cos 0 equals 1.
That's
So
right.
8 and the theta is equal to 0. So that's how you got 1, right?
That's right, because 8 times 0 is 0. Okay? 8 times 0 is 0. So cosine of 0 is 1.
Okay.
Cosine of 0 is 1. By the way, we're gonna see this really soon when I get there. If cosine of 0 is 1, anybody remember what sine of 0 gonna be?
0.
0. That's right. Okay. Shirley asks how I got the first one, namely, again, it's the special limit. It follows directly from the special limit. As long as you have sine of something and you have that exact matching pair on the bottom as theta approaches 0, the limit goes to 1. It's your special limit rule.
I kind of give up because theta is going to 0, right?
It's a special
So-
limit. So as long as, again, whatever's in the denominator and whatever you have inside the parentheses, as long as they match, as long as you have a matching pair, as theta goes to 0,
Oh,
this whole thing is going to go to 1.
okay, got it.
Anybody else?
Basically, that's like a substitution, like x would be equal to 4 theta in the
That's
sine
right.
over
That's
x.
right. That's right. Anybody else? Okay, let's continue. On to problem number 7. So, problem 7 states compute the following limits, or just limit. Oh, my bad. I moved this around too much. There we go, fixed it. So, we have the limit as x approaches 5 of x squared minus 7x plus 10 over 25 minus x squared. So, what type of method can I use to help me with problem 7?
Factoring.
Factoring, that's right. So you could factor the numerator. If I factor the numerator, x squared minus 7x plus 10, what are two numbers that when you multiply them, that gives you positive 10 that adds up to negative 7?
-5 and -2.
So you get x minus 2, x minus 5. Now the denominator, which is 25 minus x squared, how would I factor that?
X minus 5, x plus 5.
Close, but no cigar. Unfortunately, it is. I mean, it
The
is a
x
difference of two
negative.
perfect squares, but you got to start with the numerical value first rather than the variable. So you have to say 5. I'll write it this way. It's 5 plus x. Then you have 5 minus x. But as Ms. Chin is pointing out in the chat, you can rewrite this stuff. You can rewrite your denominator, right? For example, look at 5 plus x. Is 5 plus x the same thing as x plus 5?
Nope.
Yes. 5 plus x is the same thing as x plus 5. However, 5 minus x is not the same as x minus 5. But you can rewrite it in such a way where it does resemble x minus 5. All you have to do is factor out a -1, right? So observe. I'm going to continue writing my limit because I didn't evaluate it yet. So I'm still writing out my limit statement. Your numerator is x minus 2, x minus 5. Okay, that stays the same. But this denominator, where you have this 5 plus x, can actually become x plus 5. Now, 5 minus x, if you want to rewrite it where the variable goes first, then constant, just note that the negative would have technically went in front, right? So 5 minus x is the same as saying negative x plus 5, okay? That's true. That's right. That's right, Omar. If it was just x squared minus 25, then you would have been. We didn't have to worry about this. But because it was this particular way, we got to do a little bit of worrisome here. So 5 minus x is the same as negative x plus 5. Now I know algebraically that this x plus 5 that I have in my denominator will not cancel out with the x minus 5 that's in the numerator. But this negative x plus 5 that I wrote here, if I do just one more step of rewrite, I should be able to cancel out with the x minus 5. The rewrite that I have to do is just by factoring out a -1. If I factor out this -1, then the negative x actually becomes a positive x, and the positive 5 actually becomes a -5. Okay, so you're going to get -1. I'll put this in parentheses as well. -1 times x minus 5. Okay. Now, as long as x is not equal to 5, the x minus 5s can cancel out. And if you do this, you're going to get the following limit. It becomes the limit as x approaches 5 of the numerator is x minus 2. Remember, this denominator is not going to read as x plus 5 times x plus 5 minus 1. Instead, this is x plus 5 times -1. This is actually a multiple. It's a constant multiple. So it's -1 times x plus 5. All right? And now you can do your evaluation. Wherever I have an x, I can replace it with the number 5. So my numerator will read as 5 minus 2. The denominator reads as -1 times 5 plus 5. So what's 5 minus 2? Well, that's 3. So the numerator is going to be 3. The denominator is -1 times 5 plus 5, which is 10. If you take -1 times 10, it's -10. And you can pull the negative out actually from this entire fraction. So you get -3 over 10 as a solution. If I lost you, now is a good time to let me know.
So after you did the factoring, you just plugged in the 5, right? Because that's your
right.
limit.
After
get the
I did my
answer.
factoring, I cancel out the common factor of x minus 5, and then I evaluated my limit. Plugged in the 5 wherever the x is located. Evaluate and do any simplification if necessary.
If you would have left the x minus 5 the answers would have been different? Like if
You
you
mean
never
the 5
cancel them
minus
out?
x? I'm sorry?
Yeah, let's say you never like rewrote the 5 minus x to cancel out the
Well,
x
then you're
minus
gonna get a
5.
limit. You're gonna get an indeterminate. You're gonna get a 0 over 0 case, right?
Oh, okay.
The 0 over 0 is like a red flag. Like you know how they or it's like the baseball cap, and you know everybody screamed cap. That's cap.
Oh yeah, because if you plug in
it's
5 minus 5. Okay.
That's right. It's eventually,
Got it.
essentially, it's indeterminate. We can't say that there's any solution at that moment, but it's a red flag. So because it's a red flag, it means that some analytic method, for example, like factoring, is used to help compute the limit. You learned about other analytic methods too, like rationalizing, using the LCD, but on the final exam for sure, it's going to have a problem where it's factoring. Any other questions? Okay, I'm going to continue. Let's look at problem 8. Problem 8, on the final exam, there's only one example of this, but we could do both of them. We could do both of them quickly. We're computing the limit as x approaches infinity of a rational function, namely where you have a polynomial function over another polynomial function. So you can compare their degrees, meaning that you compare the highest powers, and say what your limit is, okay? So for example, look at the first one. Limit as x approaches infinity of 25 minus 3x to the 10th divided by 8x to the 25 plus 10. What is my power of the numerator, or what's my degree of the numerator? It's 10. The degree of this numerator is 10, so I'm going to call it m. On the other hand, what is the degree of my denominator?
25.
It'll be 25. I'll call that n. I'll call that n. So, well, what can I say about when I compare m and n, or m with n? Is m equal to n? Is it less than n? Or is it greater than n? That's right, Omar. You have that n is actually greater than m here, but if you start with the numerator first, you say m is less than n, okay? 10 is less than 25. So since the degree of the numerator is smaller than the degree of this denominator, then what would our final answer here be? Nope, not negative infinity. The limit goes to 0. It goes to 0. Right? So it goes to 0 because of this idea that m is less than n. Okay? As long as the power of the numerator is less than the power of the denominator, then the limit goes to 0. End of story. In the second example, however,
So if we was to write it just like that, we will get full credit.
you should.
Okay.
Right? As long as you
And
say what your m and
okay.
n is, I think you're good.
Okay.
Yep. Like, for example, look at this one. What's the degree of my numerator? Well, it looks like it's going to be 10 again. That's my m. On the other hand, what is my degree of my denominator?
10.
It's 10. So 10 is equal to 10, right? So m is equal to n. So when the degrees are the same, all you're really looking at here is the ratio of the highest powers, okay? So the ratio of the highest powers is namely the ratio of the leading coefficients. So what is the leading coefficient, or what is the coefficient of the x to the 10th in the numerator? It's -3. On the other hand, the degree of your denominator is 8. So when you put this together, the answer is -3/8. And you can again say because m is equal to n. End of story. You don't have to do any more work than what I showed. If you go about doing the analytic method where you use the fact that the limit as x approaches x approaches infinity, rather, my bad, x approaches infinity, of c over x, wait. Yes, x to the r power, where r is greater than 1. Is it greater than 1 or greater than 0? I think it has to be, I know for sure it's greater than 0, but I'm not too quite sure. I gotta look back in my notes if it's specifically r greater than 0, r greater than 1. But long story short, this goes to 0. Yeah, that's it. That's all you had to show, Jerry. You could have, but what I'm trying to say here is that you could have used this fact as well, and then use some analytic methods, like for instance, dividing by the highest power and simplifying it with this fact, and then you simplify it even further after you do all the limit evaluations. But this is fine. Nothing more here for you to do. Well, if m is greater than n, Omar, it's a D&E case. There's no limit. All right, so again, I'm just going to write this shorthand, m greater than n. This would imply no limit. It's a D&E case. It basically goes to infinity. But the reason why I say D&E is because, is infinity a real number? In math, no, infinity is not a real number. It's just a concept to represent values that are large in magnitude. All right, any questions? Yeah, not all cases, Omar. Only when you have a polynomial over a polynomial. If you have a radical now, you got to use the analytic method, unfortunately.
I have a question.
Go for it.
For this type of problems, like the first time I see that the power on the x is actually different, but let's say they were the same, right? Let's say it was x to the 10th power on top and x to the 10th power in the bottom. Can we just factor it out?
No, absolutely not. If you factor it out, your professor is going to do something like this. He's going to look at your paper, he's going to grab that red pen, and he's going to go like this. You can't factor it out. Why you can't factor it out is because if you look at your numerator and denominator, it's just both all the terms would have had to have an x to the 10th. They all would have had an x to the 10th in order for you to factor it out. But in particular, it's a sum and difference of different terms here. Right, so the greatest common factor between all these terms is technically 1. Okay, so you can't just pull the x to the 10th out of it.
I have a
Sound
quick
good?
question.
Go for it.
Do we have any more limit questions?
I have one more actually. I have two more.
Okay.
I have two more limit problems.
Are they going to infinity?
No.
Okay, because that was going to be my question. Isn't the whole point of evaluating the limit to infinity is to determine if it's like a positive or a negative infinity? as well?
No. You see, if you was doing strictly with a polynomial rather than a rational
Okay.
function, then you're looking at what something called in pre-calc the leading coefficient test, where it gives you the end behavior of a function. Right? That's what the limit as x approach infinity does, by the way. It helps you compute something called a horizontal asymptote, end behaviors. But in this case, you're just evaluating a limit as x approaches infinity of a rational function. Essentially, in the first equation, or for the first rational function, it has a horizontal asymptote at y equals 0. On the other hand, the second limit that we compute has a horizontal asymptote at -3/8.
Yeah, I see that. Thank you.
Yeah, for a better visual, you can graph the function on a software like GeoGebra, and you can visually see where that asymptote is going to be. Again, it's the end behavior that you're computing.
Thanks.
You're welcome. All right, let's continue. So, problem number 9 now states, find the value of k such that the following function is continuous for all x. One thing to note about continuity of a function, well, there's 3 things to know, right? If your function is continuous at x equals a, then 3 things must happen, right? The first thing is that the function has to be defined at a. In other words, f of a is defined. Meaning when I plug in the value of a, I'm getting back a real number. Another thing to note is that when I compute a limit this time, the limit as x approaches a of f of x is equal to L must exist. A limit must exist. It must go to a single finite real number. And the third checklist is that f of a is equal to L. In other words, 1 is equal to 2. The thing about this problem here is that we're not checking for continuity at some value. Instead, we're trying to find the value of k that's part of the piecewise function that will make this function continuous for all x. So I'm not going to show you the checking part, but I'll show you how to get the answer part, okay? The check part would have been, once you get the value of k, you rewrite your piecewise function and then go through this checklist. But again, I'm only going to go through how to get to it. All right, so as I mentioned here, here's your 3 properties. The most important property here is that a limit must exist, right? In order for a limit to exist, namely from either side, the limit from the left must always be equal to the limit from the right. So that's our starting point to solving this problem, right? We're going to write out this statement. We say the limit as x approaches a from the left of your function, f of x, must be equal to the limit as x approaches a from the right of f of x. Now, the value of a is going to be, in the case of this piecewise function, where the rule or your domain changes. So at what value of x is your domain changing at?
0.
0, right? The domain is changing at x equals 0. So we say the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x. Now from the left, which equation are we going to be using? The top equation or the bottom equation? If we're approaching 0 from the left, we use the top equation. We use the equation 3 sine of x plus 2k e to the x. So we get limit as x approaches 0 from the left of 3 sine of x plus 2k e to the x. This is equal to the limit as x approaches 0 from the right of 5 cosine of x minus 4x cubed. Okay, now to solve for k, hold off on your question real quickly here, Shirley. To solve for k, all you got to do is just plug in, evaluate the limits, right? Plug in your zeros. All right, replace x with zeros. So this will give us 3 sine of 0 plus 2k e to the 0 is equal to 5 times cosine of 0 minus 4 times 0 cubed. And now you simplify this. We talked about this earlier. What's sine of 0? 0. So 3 times 0 is going to be 0. Right? This is all going to be 0. Now, what's e to the 0? We talked about this earlier as well. It's 1. So if that's going to be 1, then I'm just left with 2k. Okay? That's going to be 2k equals 5 times cosine of 0. Cosine of 0 is 1. 1 times 5 is 5. So you get 5 minus 4 times 0, that's just 0, right? So really what we have now remaining is 2k equals 5. And once you get k by itself, that's your final answer. So if the equation states 2k is equal to 5, then k must be what value? That's right, 5 over 2. And that's your final solution. That is the value of k that will make this function continuous for all x. The way to check it out by hand is that you would have seen that basically all three of, once you plug k into your piecewise function, and you check for continuity at x equals 0, then you'll see that this is all true. And by the way, it's true that this function is continuous for all x, because none of these functions here, like for example, sine of x, cosine of x, x cubed, e to the x, none of these functions have domain issues. So k equals 5/2 is the value that when x is equal to 0, where again the left hand limit is going to equal to a right hand limit. The limit exists. In particular, when that limit exists, L is going to be precisely whatever the first equation is going to be when you plug 0 into it. Okay, you'll have your f of 0 value. Questions?
Yeah, I have a question, Professor.
Sure, go for it.
So how do we you see when x goes to 0 from the negative side?
Uh-huh.
How did we determine that was going to be the first equation, 3 sine x?
Oh, the reason why is because look at your inequality symbol. Your inequality symbol says that x is less than or equal to 0. So if x is approaching 0 from the left, then you're looking at values like -1, -0.5, -2, -0.25, -0.1, -0.001, and so forth. On the other hand, I know that the right-hand side of the equation is going to be limited as x approaches 0 from the right, because if you're approaching 0 from the right, then those values of x must be bigger than 0, okay? Like 1, 0.5, 0.25, 0.1, 0.001. They're all positive values. They're all bigger than 0.
Got it. So once we set them up, we just substitute x with the value, right?
Mm-hmm.
In this case, it was 0, and then just solve normally.
Mm-hmm.
Okay, thank you.
You're welcome. Anybody else? Any other questions? All right. I'm going to keep going. We're now officially at the halfway mark. We're going to do problem 10. So problem 10 states, find the derivative of the following function using your limit definition of a derivative. So we have a quadratic here going on. F of x equals 2x squared minus 5x plus 9. So in this problem, our limit definition is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by an h, as long as h is not equal to 0. The way that I do this is first, I figure out what's my f of x plus h, and then I make some substitutions, right? I make some substitutions, I simplify the difference quotient, and then I evaluate the limit towards the end to get my derivative. By the way, if I use my derivative rules only to solve this problem, and I'm not using this formula that I show you here, then you're not going to get no credit for this question. You have to use the limit definition. So, if f of x is 2x squared minus 5x plus 9, first thing is you get your f of x plus h. Well, f of x plus h would imply that wherever I see an x, replace it with that expression, right? The expression of x plus h. So this becomes 2 times x plus h squared minus 5 times x plus h plus 9. Now the x plus h squared, you can expand that out. You can say that you have 2 times x plus h times x plus h. I was going to rewrite the rest of the stuff. Well, actually, I could distribute the negative 5 here. Get negative 5x, negative 5h plus 9, so that way I don't have to keep writing out negative 5 in parentheses, x plus h plus 9. But more importantly, going back to the x plus h, sorry, the screen, there we go. Going back to the x plus h times itself, you can expand this out by foiling. So you get 2 times x is x squared, x times h is xh, hx is the same thing as xh as well, and h times h is h squared. Okay, now inside that parentheses, you can combine like terms, namely the xh's. You have 2 of them, so this is x squared plus 2xh plus h squared minus 5x minus 5h plus 9. And now you could distribute the 2 at the end, or inside the parentheses. So this is 2x squared plus 4xh plus 2h squared minus 5x minus 5h plus 9. Okay, now that I have the f of x plus h piece, I can go ahead and simplify the difference quotient. While I'm doing this, I'm going to write out my limit statement. So we have the limit as h approaches 0 of, in the numerator, I keep the f of x plus h terms separated from f of x using a bracket. So we have in brackets, in the open bracket, 2x squared plus 4xh plus 2h squared minus 5x minus 5h plus 9, close the bracket, minus the original function, 2x squared minus 5x plus 9, all divided by an h. So whatever terms you have in common, you can get rid of them. For example, since they both have a 2x squared, I could get rid of it because that minus sign allows me to, namely the minus sign that's between the 2 brackets here. Another term that I could get rid of is negative 5x, and I could also get rid of the 9. Essentially, all the terms of the original function gets eliminated. That was precisely 2x squared, negative 5x, and positive 9. The terms that you have remaining are the terms that include an h, so it's 4xh plus 2h squared minus 5h, and all of that gets divided by an h. Now, again, because all the terms in the numerator will contain an h, you can factor it out and cancel it out with the one that's on the bottom, right? So it's the limit as h approaches 0 of h, in parentheses, it's 4x plus 2h minus 5, all divided by h. As h is not equal to 0, the h's are canceled. And now you're ready to evaluate your limit. You have the limit as h approaches 0 of 4x plus 2h minus 5. As h approaches 0, the 2 times h, or 2 times 0, becomes 0. And you're left with 4x minus 5. And that is precisely the derivative of this function. Omar, for the final exam, I want to say yes. If you can't factor out an h somehow, then you can assume that you did something wrong. That's like another cap. That's like another red flag. Any questions?
So you,
Say it again. Okay. I guess we'll continue. We'll keep going. So although I was only aiming or shooting for this workshop to be for 2 hours, I'm gonna keep writing it out. I'll keep going. Okay. So if any of you have to leave because it's already been 2 hours or we're approaching the 2-hour mark, I understand. Just note that we're gonna have this. We're having this recorded. It's gonna go on YouTube, and our YouTube link could be found on our website. Okay. In particular, if you're here now, I'm just going to just paste the link here. So that's the playlist link that I sent you of the the original sample final. All right, let's keep going. You see me on Twitch. Come on, Twitch. Raphael's on Twitch, not me. Yeah, this will be the only review session, unfortunately, Jerry, but you can definitely come to the MAT Center. You can definitely come to the MAT Center, and I'll be able, starting this Monday, we could be able to help you out. All right. Oh, I'm there every Monday through Wednesday from 11 to 7. 11 to 7.
Can you say that again?
Say what again?
Like I didn't hear nothing you said.
Nope. Well, I said a whole mouthful. I just said that if, in short, if you have to go, that's fine. Just note that the meeting is recorded. So, whatever you miss, you will find the recording on our YouTube page. Francisco, yes, I'm going to be there on actually this Tuesday and Wednesday. I'm only going to be up there till like 4 p.m. actually, because I got to come back home and do the review sessions for the other courses, namely statistics and pre-calc.
So on Wednesday we could come to you at 11 a.m.
Yeah, you can. I'm cool with that.
Okay. I have a question that has nothing to do with this. Is the are the labs open so I could use the computer to finish like my lab work?
like if you want to come in, well, on Monday you could come in from 11 to 7, that's fine. But on
Mhm.
Tuesday and Wednesday, probably will be open until 4.
Okay, thank you.
You're welcome. Right now, the censor is being run by a 2-man show. The host of this meeting, Raphael, and me, the co-host. It's a 2-man show, 2-man operation, all semester long. All right, let's continue. So here's the second half of your final, and we're going to start with problem 11. The volume of a cube decreases at a rate of change of 0.5 cubic feet per minute. What is the rate of change of the side length when the side lengths are 12 feet? So first of all, when I look at the volume of a cube, do anybody know the formula for the volume of a cube? We say that the volume is equal to what?
S squared.
Careful,
mean,
that's
cube,
a
cube.
square.
My fault. Yeah. Cube.
Cube. That's right. Now, another piece of information that was given to us is that the volume is decreasing at a rate of 5 cubic feet per minute. So because it uses the word decreases, I know that this rate of change should be a negative value, right? It should be negative 0.5, or you could just say it as negative 1/2. I'm going to use negative 1/2 here. But this negative 1/2 has to equal to a rate, the rate of the volume. How do I write out the rate of the volume mathematically, or using calculus notation? That's right, Andrea. It's going to be dV dt. Now, another thing to note is that the question now states, what is the rate of change of the side length, right? What is the rate of change of the side length? So what is the rate of the change of the side length? That has to be ds dt when s is equal to 12, okay? So all I did here was just write out all the information that I extracted from this problem. Now we're going to do the calculus. The calculus is only one line, actually. The calculus step is to take your derivative. However, when I take the derivative of the formula, or our equation, v equals s cubed, I take the derivative with respect to what variable? That's right, Omar, it's t. There you go, you got it. You make Raphael proud. All right, so when you take the derivative with respect to t here, you're going to get dv dt is equal to the derivative of s cubed with respect to t. So this is implicit differentiation, right? The derivative of s cubed is 3s squared, but again, the variables don't agree, so you say ds dt. All right. This problem required us to find ds dt, knowing that dv dt was negative 1/2, and s at this moment was equal to 12, or 12 feet. So we're going to get, when I plug in the values, negative 1/2 equals 3 times 12 squared ds dt. All right, what's 12 squared? $144. Now, if I take 144 times 3, that's going to be equal to what? 432. So we have 432 ds dt. Okay, now the thing is, if I wanted to rewrite this, namely getting ds dt by itself, I would have had to divide by 432, right? But if I divide by 432, an equivalent way of saying this is that you're multiplying by 1 over 1 over 432, right? So ds dt is going to equal to the negative 1/2 times 1 over 432, right? Dividing by 432 is the same thing as multiplying by 1 over 432. That should be a little bit of a refresher when you were doing U-substitutions for integration, which I'll get to at the end. So negative 1/2 times 1 over 432, well, that's negative 1 times 1, which is negative 1. And then 2 times the 432 should have been 864. So our final answer is going to be negative 1 over 864 feet per minute. And that'll be a solution. And that's it. The thing about this problem is that when I word it, I didn't word it the way that I wanted to. So please be mindful that you should look over problem 11 on the original sample final, because it has this extra condition. The extra condition is that usually they give you the volume of a cube, right? They'll give you the volume of the cube or whatever shape you're dealing with. And in the case of the cube, you have to first figure out the side, right? So like, for example, if the volume was equal to 27, right? Like, this is a quick example. Suppose the volume was equal to 27, then what would be the value of the side of the cube? It would be 3. That's right. So if volume is equal to 27, then S would have been 3. So again, just keep that in mind, that usually in this problem, there's an extra condition that says, okay, if volume is 27, first you got to find out what's the value of S before you could do some calculations. All right.
I have
Any
a question.
questions? Go for it.
So how, if the volume, let's say just say it was 27, how would the S value be 3?
Because if volume is equal to 27, and I know that the volume of a cube is equal to S cubed, or S to the third power, then I would have had to set S to the third equal to 27. And if I do that, when I take the cube root on both sides, you get S equals 3. Because 3 times 3 times 3 is 27.
Oh, got you. And then for the negative 1/2, you just got that because it was 0.5 feet, right?
That's right. But be careful when you read that statement just now back to me. How did I get the negative? What gives it away that it's a negative rate?
That I was gonna ask, because when you were going over it, I didn't hear.
It's all
It's
good.
decreasing.
It's decreasing. The key word was decreasing.
So if it would have said the volume of the cube is increasing, and would just been 1 over 2.
Yeah, it would have been a positive
Okay.
1 over 2. Yep.
And that goes for any number, correct?
Yeah, that would have went for any number. If it says decreases, it's negative. If it's increases, positive.
Got you. Thank you.
You're welcome. Anybody else? Any other questions? All right, let's go on to problem number 12. Problem number 12 states, find all the intervals where this graph y equals 2x cubed minus 7x squared plus 11x plus 22 is concave up, concave down, and you're finding all the inflection points. So because it states concave up, concave down, and inflection points, or point of inflections, how many derivatives is required to solve this problem? 2. Yeah, that's right. You need 2 derivatives. All right, so our original equation was y equals 2x cubed minus 7x squared plus 11x plus 22. So just be mindful, by the way, that just a little side note here, that your domain of this function is all real numbers, right? It's negative infinity to infinity, okay? Usually this is like a step omitted because anytime you're dealing with a polynomial function, this is true. Your domain is all real numbers. But anytime you have a function with domain issues, it's important to state your domain. You probably would have seen that when you were doing some of your homeworks on MyLab. Like if you use Pearson MyLab for your homework, you would see that sometimes, that you had to first know your domain. Okay, now let's go ahead and do the calculus steps where we get our derivatives. So if again, we know what the original function looks like, what would the first derivative be now?
It's gonna be 6x squared minus 14x plus 11.
Uh-huh. Now, you can go ahead and get your second derivative. So what would the second derivative be?
12x minus 14.
That's right, 12x minus 14. So if you want to find any possible inflection point, you set the second derivative equal to 0, right? Another thing you got to check for usually is if whenever the second derivative doesn't exist for some value of x that's in your original domain, but we don't have to worry about all of that here because we're dealing with polynomials. To avoid any confusion, just got to set this derivative equal to 0, or namely the second derivative. So you got 12x minus 14 equals to 0. You add 14 to both sides, you get 12x equals to 14, and therefore x will now equal to 14 divided by 12. And you could reduce this number, right? X, reducing this fraction will be 7/6. So I'm not going to confirm that this is a guaranteed inflection point. I'm just going to say that it's a possible inflection point, right? The reason why I'm saying that it's a possible inflection point is because as long as the concavity is changing to the left and to the right of this value, then it's going to be an inflection point. But if the concavity never changes, like let's say on both sides it's concave down, or both sides is concave up, then unfortunately this will not be an inflection point. So when I want to do the concave up, concave down stuff, I create a table, right? So I'll put my table on this other side. The first thing that in your table should be your intervals, the intervals of interest. So the intervals that I'm looking at here is, well, if my domain is all real numbers, negative infinity to infinity, and I only have this one possible inflection point, then I'm splitting this interval, this one interval, into two. The first interval will go from negative infinity to positive 7/6. And my second interval goes from 7/6 to infinity. Now for each interval, I got to come up with a test value. So from negative infinity to 7/6, can somebody give me a test value?
0.
0? Yeah, 0 works. You can definitely use 0. And from 7/6 to infinity,
2.
you can use the number 2. All right, so now what I got to figure out are the signs of y double prime at my test value. All right, so if I plug 0 into my second derivative, then we get 12 times 0 minus 14. Well, 12 times 0, 0, 0 minus 14 is negative 14. And comparing that to 0, is it less than or greater than 0?
Less than?
Yeah, it's going to be a less than. You got negative 14 is less than 0. So one conclusion that you can make about this first interval is that it's going to be what? Concave down or up? Down. Concave down. If it's less than 0 at your test value, then it's concave down. Okay, let's see what happens when I plug in 2. We get 12 times 2 minus 14. Well, 12 times 2 is 24. 24 minus 14 is 10. So is 10 less than or greater than 0?
Greater.
It's greater than 0. So this is going to be
Concave.
concave up. So did the concavity change to the left and to the right of your possible inflection point? Yes, it did. So we could just write that out. We can say that, okay, from your table, you don't have anything else to write out because it summarized the intervals precisely that's concave up and down. But now what you can write out is that there is an inflection point. There is an inflection point at x equals 7/6. The thing is, you only have 2 hours to solve or complete this final exam. So even though it says inflection point, where you would have technically had to find a y value, for this problem, trying to go about solving for y here would have been meaningless. Just say that an inflection point is located at the value that you found earlier, which was 7/6. Questions?
Yeah, just one question. How did we determine the test values to be 0 and 2?
Because they're contained inside of those intervals, right? If you think about your number line, right, our domain was from -infinity to infinity. So somewhere on this number line, let's say your center is 0, then 7/6 should be somewhere here, right? This value here is 7/6. So from -infinity to 0, or -infinity to 7/6, 0 is a test value because it's in the interior of that interval. On the other hand, from 7/6 to infinity, inside of that interval or in the interior, you have your test value of x equals 2. You don't have to use 0 and 2. You could, as long as you determine test values that are in the interior, inside of those intervals, you can use any value. I could have used -10 and +10. Right? Any other questions? That's a good question. We have to be mindful of reducing fractions due to their decimal values in other case of complex equations. I wouldn't write these values in decimal form. Just leave it the way it is as a fraction. Yeah, just leave it as a fraction. Reducing the fraction is a little helpful because you can sort of easily, more or less easily determine what values of x goes in each test and figure out the test values per se.
It says find all inflection points. Will we lose points if we only find that like main one?
No, that was the only one. You see, if you think about it, look at your second derivative. Look at the equation, 12x minus 14. That's what type of equation, Carlos?
That's a polynomial.
It's a polynomial. More specifically, what type of
Only
polynomial?
one.
Degree 1 it's linear. So that means there's only one solution.
Oh yeah, that's true. If it was like x minus 4 and then x plus 3, like a binomial, then yeah.
You'd have had a quadratic, would have been like a binomial. That's right.
And then you
That
would have
means-
to find in between.
That means there would have been up to at
Right.
least 2. I mean, at most 2 inflection points.
But then you would have to find concave up between -infinity and the first point, that point, and 0, 0, and that point.
That's right.
point
That's
to
right.
infinity. That's like 4, right? Which does happen.
It does happen. Yeah, it
Okay.
depends on whatever the degree of your second derivative is. If your second derivative has a highest degree of like 5, then there's at most 5 inflection points, and that will start getting crazy on us, you know.
Yeah, that's what I was confused with. All right, thank you.
You're welcome. Here's another way to look at it. If you have depending on the number of inflection points, it's your intervals is always one more than the number of inflection points. Like for example, if I had one inflection point, then there's two intervals. But if there's two inflection points, then there's three intervals, right? So that's the pattern. There's always one more interval than inflection point if you count them. All right. Any other questions? All right, let's continue. Here's problem number 13. Problem number 13 now states find all relative max and minimum values of this function. F of x equals x to the fourth minus 5 minus 8x squared. There's a couple of different tests that I can use here, right? What are some of the tests that you learned about finding relative extrema? There were two in particular that you can use. Does anybody remember them? If you're going to go about doing that, Miss Chin, that means that when you say find f prime of x is equal to 0, that implies that you're going to use a first derivative test where you locate critical values. Which is okay. Yes, we have to find critical values. But you don't have to always just use the first derivative test. In fact, you can use something called the second derivative test. So I'll show you how to use the second derivative test here as we go about this problem. So first of all, because I said I'm going to use the second derivative test, I need a total of two derivatives. So if f of x is x to the fourth minus 5 minus 8x squared, then what would be f prime of x, our first derivative?
Would it be 4x to the third power over 5 minus 16x?
There you go. That's your first derivative. 4x cubed over 5 minus 16x. Now let's get our second derivative, f double prime of x. Well, what will be the derivative of now 4x cubed over 5?
It should be 12 x squared over 5 minus 16.
That's right. You get 12x squared over 5 minus 16. All right, good. So we got our two derivatives. But again, just keep in mind, I'm going to use the second derivative test. Little f surely would have been, just my notation, little f is this big F right now, right? The function name was capital F of x equals x to the fourth over 5 minus 8x squared. So that's why the derivatives are capital F prime, F double prime. Okay, so now we go ahead and we find our critical values. So if you want to find your critical values, you set the first derivative equal to 0, just like what Ms. Chen mentioned in the chat. So I'll start from the bottom here. what we have is 4x cubed over 5 minus 16x equals 0. Now, solving for x here is not that easy, or trying to solve for x here is not that easy, only because that very first term contained a fraction. One of the things that we do with equations that involves a fraction that drives us insane is that we clear it. We clear it by multiplying by everything by their least common denominator. Since there's only one denominator, namely that 5, all the terms are going to get multiplied by 5. So for example, if I take 5 and I multiply it by 4x cubed divided by 5, what would happen to your 5s?
It will cancel out.
They'll cancel out. I'm not there yet, Shirley. I'm not there. When I say that I'm going to find an antiderivative, I'll let you know, okay? This is just notation. I'm not using any definitions regarding antiderivatives yet. This is just, there's no mentioning of antiderivatives as of yet. Okay, so yes, the 5s were canceling out, so you have 4x cubed. Then what's 5 times negative 16x? 80x, so this will be minus 80x. And 5 times 0 is going to still be 0. So good. That's good news. We were able to clear out the fraction, the denominator of the 5. Now I'm going to factor this. What can I factor out from 4x cubed and the 80x?
X.
There's more than an x that I could factor. I could factor out a 4x. So if I factor out a 4x, we get x squared minus 20 is equal to 0. And now I could split this into 2 equations, all right? So when I do split this into 2 equations, this will give us 4x is equal to 0, and we're going to get x squared minus 20 is equal to 0. So for the equation that says 4x is equal to 0, then x must be equal to what value? Yeah, that's going to be 0. X has to be equal to 0. On the other hand, with the equation of x squared minus 20 is equal to 0, I can add 20 on both sides. I can say that this is x squared is equal to 20. And then how can I get rid of the square from x squared?
Square root to 20.
Square root both sides, right? You need the square root. But just be careful here, because if I take the square root of both sides, then I get x is equal to plus or minus the square root of 20, right? In other words, when I square the positive square root of 20, that will give me 20 back. In addition, if I were to square negative square root of 20, that still gives me back a 20 as well. So x is equal to 2 solutions here, plus or minus square root of 20. But more importantly, these now are the 3 critical values, right? So the critical values here are x equals 0, x equals negative square root of 20, and x equals square root of 20. After you find your critical values, you can go ahead and apply the second derivative test. If we apply the second derivative test, what we're going to get is the following. Again, each of these critical values, I got to plug it into the second derivative. So this is going to be f double prime of 0. So this is 12 times 0 squared over 5 minus 16. Now, if I work out the computation here, what would be my solution? negative 16. And what do I know about negative 16? Is it going to be less than or greater than 0?
Then
Less than. Yes, less than. It's less than 0. So because we get less than 0 here, this is going to be a relative max. So I'll write out the summary at the end, but just keep in mind that because it's less than 0, it's a relative max. All right, let's look at what happens now with the negative square root of 20. Well, when I plug in negative square root of 20 into our second derivative, we get 12 times negative square root of 20 squared minus 5 divided by 5 minus 16. If you work out the computation here, you can obtain the value of 32, right? Because negative square root of 20 squared is 20. 20 divided by 5 is a little bit easier to do. 20 divided by 5 is going to be 4. Then 4 times 12 is 48. So 48 minus 16 is 32, which is greater than 0. And if I did this again with the positive square root of 20, it's the same thing as the negative square root of 20, because both of these critical values are getting squared. So you're going to get 32 here. Oops. Which is also greater than 0. So now you write out your summary of the second derivative tests. So again, because at the first critical value, you have that, again, when you evaluate it into your second derivative, it was a less than 0, then this is going to be a relative max. So we say relative max of f of 0. So if I want to figure out what that value would have been, I would have had to plug 0 into the original function. But for time constraint here, I'm not going to do so. I'm just going to say relative max of f of 0 is, at x equals 0. Also, by the second derivative test, when I evaluate the other two critical values, we got that they were both positive, which implied greater than 0. So they're both minimums. So we say relative mins of f of negative square root of 20 and f of square root of 20 at x equals plus or minus square root of 20. All right, so that was the second derivative test used to solve this problem. Even though it says find all relative max and mins, I think it's more important that you can locate where they are. Right? I don't think your instructor is going to ask you to really find what f of 0, f of negative square root of 20, or f of square root of 20 are going to be. They're more interested in where are the relative max and min values are located. Relative max is different from, relative max is the same as local max and mins, but absolute is different. Absolute means that when you look at a graph on a particular closed interval, you can have the smallest and largest values. It doesn't necessarily have to happen at your critical values, they can happen at the endpoints. But
so
relative extrema, they occur, my bad, Carlos.
I cut you off, I'm sorry.
The relative extrema occurs at your critical values. Okay, Omar? They occur at the critical values because if you think about mountains or valleys, right? Let me just draw some mountains. There's a mountain, there's a valley. You could have different mountains. You could have something that's peaked, something that's not peak, like this one. These are all considered to be where you have critical values, where it's relative max and mins. But absolute max and mins, they can possibly occur at endpoints. The ones that are smooth and rounded is whenever the critical values was found by setting a derivative equal to 0. The ones that are sharp and peaked are whenever whenever the derivative does not exist at some value. All right, Carlos, you had a question. What was it?
Oh, I said, could we have, like, when we got the critical values, could we not have just plugged those into the 4x over 3 over 5 and found it that way, or no?
No, because that gives you back 0.
Okay.
You can't plug back the critical values into the first derivative. However, if you plugged in the critical values into the second derivative, and it says that, or when you do the evaluation and you get back a 0, then the test is inconclusive. Then the test is inconclusive.
So for the second derivative test, if
Mhm.
it's a negative, that would make it a relative maximum. So it would be the opposite, as if it was like increasing or decreasing. So, like, you know how when you concave, if it's a
Yes, and
negative,
I know what you're
it's
implying.
concave up. Oh, okay. Thank you.
You're welcome. Anybody else? Any questions?
Oh, also, can we put, instead of like f of 0, is f of x at x equals 0 the same thing, or f of x at x equals positive or negative square root of 20? Is that the same answer?
No, because then x is technically could be any value, right? You want to say x is specifically. I mean, I can see your point there, but it's probably better just to write f of 0, f of negative square root of 20, and f of square root of 20.
Okay.
Anybody else?
I have a question.
Sure.
I
No.
get confused right now because our professor, when he in this problem maximum and minimum, he blocks the number in the derivative number 1, not 2.
Wait, say that all over again. He blocked the number, huh?
Yeah, in the derivative number 1. We didn't use derivative number 2 here.
Oh, you're talking about he used the first derivative test.
Yes.
Oh, by all means, if he uses the first derivative test, then you can also use the first derivative test. For me personally, I just go with the second derivative test. However, if I do any evaluations like what I did in that upper right hand corner, and I see that I get something that's like a 0, then that's no good, because then I have to go back to the first derivative test.
That's mean it's okay when we use the
Yes.
second.
Yeah,
Oh, okay, got it
so
right now.
either one is fine as long as your second derivative test doesn't come out with any inconclusive information, namely when you plug in a critical value into the second derivative and it gives you back a 0.
I thought only when we try to find the concave up and concave down, we use only the second derivative.
No, not necessarily.
Oh, okay, I got it right now.
But concave is different from relative max. That's what I have.
That's right. It's different.
Yeah. Thank you.
You're welcome.
Concave is how the derivative changes versus max and min is how the actual function changes.
That's right. All right. First derivative test just, measures the rate of change of the function. Concavity measures the rate of change of the first derivative. If you want to look at it that way, it's exactly what you said, Omar. Not Omar. That was I'm sorry. Who was that? That wasn't Omar. That was Carlos. Carlos, by the way, you got a job? Working? Are you working at the moment?
I literally just got hired. We could talk about it. You met me today in the staircase.
Yeah. We'll talk. Oh, that's you. Oh.
Yeah.
All right.
The guy that like when you were, when we were going to the basement, that was me.
Yeah.
With the green shirt.
Yeah, I remember. Don't worry, I remember.
We could talk about it.
Yeah, we'll talk.
Or you,
Alrighty.
or you can email me.
Yeah, definitely. Or you just come see me in person.
That's fine.
All right, let's continue. We're up to problem 14. 14 states, find the absolute max and minimum values of your function on this closed interval. Okay, so now that we're dealing with absolute max and minimum, and we're dealing with on a closed interval, one thing to note is that the absolute max and mins, they can occur at the critical values or at your endpoints. But be careful, your domain of interest here is 0 to 5. Let's look at what happens. So, what happened to my pencil? Don't die on me. All right, did it. Oof. All right, so we have f of x equals x cubed minus 12x. Let's look at our first derivative. What would be the first derivative of our function here? You get 3x squared minus 12. All right, now what you can do is take this first derivative and set it equal to 0 to get your critical values. All right, so we have 3x squared minus 12 equals to 0. And you should be able to solve this by factoring, right? For example, from the 3x squared minus 12, what can I factor out from it? A 3. You can pull out the greatest common factor of a 3, which is x squared minus 4 remaining. Now, the x squared minus 4, you could break that down even further, right? It's a difference of two perfect squares, so it becomes x plus 2 times x minus 2 equals to 0. All right, so you divide by 3 on both sides just to get rid of that constant multiple. It doesn't have any effects to this problem because when I divide both sides by 3, on that right-hand side, you still get 0. So we have x plus 2 times x minus 2 equals to 0. When I solve for x, there should be two solutions. We're going to get x equals some number, and we're going to get x equals another number. So what will be the values of x here?
-2 and +2.
Yeah, you get x equals -2 and x equals +2. Is there any issues with our critical values here?
Yes, the -2.
The -2. Look at your interval of interest. Your interval of interest is from 0 to 5, okay? So because -2 is outside of that interval, we're going to reject this value. The only one we're going to accept is x equals 2, okay? It might not happen on your exam, right? It's a possibility that you don't reject anything at all. Both critical values are in the closed interval. But if that were to ever happen, just note that if one of them is not inside of the interval, you reject it. So, with that being said, you only evaluate the original function at the endpoints and that one critical value that I put a box around, x equals 2. All right, we have f of 0 to compute, f of 5, right, that's your endpoints, and then f of 2. So f of 0 is the easiest one to compute because if you do 0 cubed minus 12 times 0, that's 0. F of 5 would mean 5 cubed minus 12 times 5. So 5 cubed is 125. 12 times 5 is 60. So 125 minus 60 is 65. And then f of 2 would be 2 to the third minus 12 times 2. So what is 2 to the third? Well, that's 8. 12 times 2 is 24. So 8 minus 24 is -16. And now you do your comparisons. Which one is the absolute max?
65.
So we say absolute max of 65. Oh, my bad. At x equals 5. And then you have an absolute minimum of -16 at x equals 2. That's the minimum. And that's it. Questions?
Yes.
Go ahead.
So how come the absolute value of 65 is at x equals 5.
Because it's possible, again, when you're dealing with a closed interval, it's possible that the absolute max and mins can occur at the endpoints. Right? So for example, let's say I drew a curve, it looks something like this. Let's say I had 2 endpoints, let's say one here, one there. And let's say I have something like this going on that endpoint. Then here, at this value, at the right endpoint, is where you have your absolute max. Because of that closed interval of interest, at the very end is where your max, you have your top dog. That's the absolute max, the biggest value. On the other hand, here's a critical value somewhere down here. And around this area, at that point, you will have your absolute minimum. And it occurred at the critical value of whatever that function is. Okay, so it's possible that on a closed interval, that at one of the endpoints, you have either an absolute minimum or an absolute maximum, or it could possibly have both. There's like different pictures you can draw. You don't have to just be subject to this one picture. Sounds good?
I'm still a little confused.
Why? What's confusing? What part makes it confusing?
How we ignored 0 on the closed interval and we chose 2, x equals 2.
No, we didn't ignore 0. Think about it. Is 0 going to be a minimum value here?
No. Oh, okay. I see what you did. Okay. I got you.
Look at your output values. 0 is not.
I got it. I got you. It's just okay. It's just a number we plugged into the function to get. Okay, I got you.
If you want, you could write out these words to help you. Here's the largest, and here's the smallest. Right? Largest is absolute max. That's the top dog. Smallest is a small dog. It's like, if you think about baseball, that's like not even AAA. Not, you're in the minor leagues, you're in the farm system, but you're all the way at the single A.
Got it. And let's just say the -2, we didn't reject it at this point, right? We didn't reject it. We will also have to plug it in as well, correct?
That's right. Like, let's say if the closed interval was from -3 to 5, then I would have had to plug in -3, -2, 2, and 5. What happens at -3? What happens at -2? We don't know at this moment, only because it wasn't of the interval of interest for this problem.
Got you. And we didn't use -2 because it was smaller than our closed intervals, correct?
It wasn't inside of the closed interval.
Okay, like in the range?
Yeah, it wasn't in the range.
Okay, got you.
That's right. That's why you reject it. All right. Anybody else? Okay. Let's go on to problem number 15 now. Problem number 15 is where we get introduced to antiderivatives. And essentially, we're working backwards here. It states that a particle moves along the x-axis with an acceleration given by a of t equals 2t plus 5, where t is measured in seconds and s is measured in meters. If the initial position is given by s of 0 equals 3, and the initial velocity is 9, then find the position of the particle at t seconds. Oops, there you go. All right, so we were given these following pieces of information. We were given a function, the acceleration function, and we were given 2 initial values. We have the initial value for position. We have the initial value for position. Okay, there's, again, the initial value for your velocity, initial position, when both t, time, was 0. Okay, so like I said, you have to go backwards. You have to first, you're given the acceleration function. So from the acceleration function, you can find velocity function. To find the velocity function, you use antiderivatives or integrals. You have to take the antiderivative of a of t dt, right? Namely speaking, you take the antiderivative of 2t plus 5 dt. So what is the antiderivative of 2t?
Two t squared over 2.
That's right. You get t squared over 2, or 2t squared over 2, plus the antiderivative of
5t
5t plus what?
c.
C, plus your arbitrary constant. Okay, so that's v of t. You can reduce this a little bit. You can say that your velocity function is just t squared over 2. Sorry, t squared rather, because the 2's would cancel out, plus 5t plus c. Now, since it states that the initial velocity is 9, then what do you think the value of c is going to be? If the initial velocity is 9, then c has to be 9. That's true. The way to justify this is as follows. You see, v of 0 implies that when t is 0, you're going to get 0 squared plus 5 times 0 plus c equals 9. But when you do the computations, what happens to the 0 squared and the 5 times 0? Yeah, that's all 0, Miss Chin. So you're left with c equals 9. And now since we're left with c equals 9, I could rewrite my velocity function. So my velocity function is going to be t squared plus 5t plus 9. And that's it. That's the velocity. Now that we have the velocity function, you go ahead and you get your position function. We say s of t is equal to the integral or the antiderivative of v of t dt. So if I take the antiderivative of this velocity function, we're going to get the integral of t squared plus 5t plus 9 dt. And we integrate once again. What is now the antiderivative of t squared? That would be t cubed over 3 by the power rule for integration. Right? You add 1 to the exponent and divide by that sum. Then the antiderivative of 5t is going to be what? You get 5t squared over 2. Antiderivative of 9. 9t. I put plus dt there. I didn't mean to say that. I meant to just say dt. And after the 9t, we have to include our arbitrary constant. So that is our position function. However, with the condition that the initial position is 3, this will tell us that s of t now is going to be t to the third over 3 plus 5t squared over 2 plus 9t plus 3. In other words, this value c here, the arbitrary constant, must be equal to 3. Right? And the same reasons, or to justify this, is like the same reasons of justifying why the velocity function, we replace c with 9. Yep. Any questions? All right, let's continue. I'm just going to scroll down just a bit, and we're going to look at problem 16. Problem number 16 states that we want to find the maximum value of xy if it is required that xy is, if it's required that 8x plus 2y is equal to 54. So in this problem, you have two equations going on. One of these equations is the primary equation. One of the equations is the constraint equation. So what do you think is your primary equation? In other words, what is the equation that we're trying to optimize? xy. That's right, Andrea. So the way that I'm going to write this equation, I just can't say xy because it's a expression. I need an equal sign. So I'm going to say that m is equal to xy. Okay. I know that when I find xy eventually, that when I multiply them, it gives me our max value, m. Okay. So therefore, our constraint is going to be 8x plus 2y is equal to 54. All right. So for the constraint equation, you're going to rewrite it in terms of one of the variables, and then you're going to make a substitution into the primary equation, so that way the primary equation is written as a single variable. So if your constraint equation is 8x plus 2y is equal to 54, I can rewrite this constraint in terms of y, right? The way that I can do this is subtract 8x on both sides. This will give me 2y is equal to 54 minus 8x. But to get y by itself, I would have to divide every single term by 2. So the 2's would cancel. It'll give me y by itself. And this will say y is equal now to 54 over 2, which is 27. And negative 8x over 2 is negative 4x. So you get y equals 27 minus 4x. All right, so we move on to the next step. After you have your constraint equation written as a single variable on one side, now you can make a substitution into your primary equation. Our primary equation was m equals x times y, but since y is 27 minus 4x, then this implies that m should be equal to x times 27 minus 4x. You can distribute the x inside of your parentheses, and this will now become 27x minus 4x squared. Okay, what do you think will be my next step here? Why would I rewrite m as a single variable? What's the purpose of rewriting this equation as just one variable here? That's right, Ms. Chen. You want to find m prime. If you want to find m prime, well, you got to get your derivative of m. So m prime is going to equal to 27 minus 8x. And now you can go ahead and take this derivative and set it equal to 0. Okay, so you get 27 minus 8x equals to 0. You solve for x. You can subtract 27 on both sides. This gives you negative 8x equals negative 27. Then you divide by negative 8 on both sides, and you're going to get x equals negative 27 over negative 8. And you can reduce this, right? 2 negatives always makes a positive. So 27 over 8 is the value of x. So now since x is equal to 27 over 8, you solve for y. Solving for y is actually not that bad because I can plug our value of x into this equation here, and I'm going to put a box around of. I can plug the value of x into this equation and again solve for y. So we're going to get y equals 27 minus 4 times 27 over 8. The 4 over 8, by the way, you can reduce that as to saying 1/2, right? Because what number goes into 4 and 8 evenly? That number would have been 4. So 4 goes into itself once, 4 goes into 8 2 times. Therefore, you get y equals 27 minus 27 over 2. What else can I do? Well, I can also rewrite the first 27 as a fraction, as 1, and then multiply it by 2 top and bottom, so that way I can combine into a single fraction. So this will become y equals 54 over 2 minus 27 over 2. And because the denominators are the same, it's 2. When I take the difference at the top, you get 27 over 2. So your solution here, right, your solution now is that the max product xy is going to be 27 over 8 times 27 over 2. The good thing is I don't have to multiply these two numbers, it's just x to find it. Well, if once I have x, once I have y, and when I multiply them, it gives me my maximum product, right? So this will be your max product. The one thing that I omitted here, by the way, justifying that this is true, that all of this is legit work that we're doing, is that you can check that the x equals 27 over 8 is a max. You can check by the second derivative test. So just aside here, you see m prime, the first derivative was 27 minus 8x. So your second derivative, m double prime, is going to be negative 8, which is less than 0 for all x. So because we found that x is 27 over 8, then that's indeed going to be a maximum. Another thing to look at it as to why we are finding a max, or how I know that this is a max, was that the 27x minus 4x squared, this original equation here, this equation, this is a quadratic. It's a quadratic that opens downward, right? It has a sad face. It's a quadratic that opens downward. So those are all key components that gives you a good indication that you're fine, that your x value is legit, that it is a max. So once you find that one value, finding the value of the second variable, it just becomes arithmetic. Any questions? Any questions? Okay. I'm going to move on to problem number 17. So from problem 17 and onwards, we're going to look at basically the beginning of calculus 2 here, right? We're going to start with problem 17, which talks about writing a 3-term Reimann sum for an integral. We're writing this Reimann sum, but just remember that you're not evaluating it. You just got to set it up, okay? You just got to set it up. So Reimann sums, in short, was just a process of estimating an area under the curve. In particular, namely, it has to have some bounds. Like, for example, is it going to be above the x-axis? Is it going to be a function that's going to be increasing, decreasing? There's like a lot of question marks, right? There's a lot of questions that can be answered with this one. But here's the formula that I'm going to write out, and I'll show you how to do it step by step. So for the 3-term Reimann sum, your integral from a to b of f of x dx is equal to delta x times the sum from I equals 1 to n of the f of x i's. In other words, you're taking the sum of rectangles, the sum of n rectangles, to compute an area under a curve, right? The sum of the area of those rectangles gives you a good approximation of the area under a curve. The delta x here, right? The delta x is the width of the rectangles. It's going to be the width. And the way that we compute this width, based off of the formula that I wrote out so far, is going to be b minus a, the upper bound of your integration, your limit of integration minus the lower limit of integration, divided by the number of rectangles. So because I'm writing a 3-term Reimann sum, then I know that n has to be 3. Yes, n has to be 3. Also, the values of b and a, again, are your upper and lower limits of integration. So b has to be 2, and a has to be 0. Now, the f of xi's is depending on the type of Reimann sums. It's the height of the rectangles. You could use left Reimann sums, you can use right Reimann sums, or you could use the mid Reimann sums or midpoint Reimann sums. What I'm going to do is use left Reimann sums. So whatever Reimann sums you want to use, that's fine, but I'm going to use left Reimann sums. Okay, so first, once we have our formula established, you find your width. The width is always going to be the same. Delta x is equal to b minus a over n, so that's precisely 2 minus 0 over 3, which is 2/3. Now, you can go ahead and find all the f of xi's using left Reimann sums. When I use the left Reimann sums, for example, I can use all the left endpoints of our region of interest, or the interval of interest, right? So for example, let's look at this line, right? This line segment is based upon your limits of integration. The lower limit was 0, the upper limit was 2. What I'm going to do is partition this line segment into 3 parts. In particular, those 3 parts have equal width, which corresponds to 2/3, right? So if I start with 0, if 0 is my first value in my partition, right? Then with the class width being 2/3, the next value that comes after 0 must be 2/3. The value that comes after 2/3 is 4/3, because I got to continually add my class width here. And then if I add another 2/3, it's the same thing. 6/3 is the same thing as 2. And because I said that I'm using all the left Reimann sums to get our heights, then the values that I'll plug in from each partition, right? Let's color it. Let's say we got from 0 to 2/3, then we got 2/3 to 4/3, and then 4/3 to 2. I'm using all the left endpoints of each partition, each parts. So I have to use 0, I have to use 2/3, and I'm going to use 4/3. Okay, so your f of xi's are going to be precisely f of 0, f of 2/3, and f of 4/3. And now I just set up my integral, right? So I set it up, but I don't evaluate it. I can do a little bit of evaluation, but not too much. So again, the formula states that you take delta x, right? Your Reimann sum, again, it's a 3-term Reimann sum. You start off with your width. The width will be 2/3. So the 2/3 go on the outside, And then the inside, you have all of your heights. If you want to figure out what those heights are, then I got to plug 0, 2/3, and 4/3 into my function. My function here was 2e to the x plus 7. So if I plugged in 0, you get 2e to the 0 plus 7. And again, I'm going to leave that alone. That will be the height of the first rectangle, plus the height of the second rectangle is going to be 2e to the power of 2/3 plus 7. And then the height for the third rectangle is 2e to the power of 4/3 plus 7. And that's it. That is your Reimann sum, right? 2/3 was the height. The values that are inside the brackets, like 2e to the 0 plus 7, then 2e to the power of 2/3 plus 7, then 2e to the power of 4/3 plus 7. Those are the heights of each single rectangle where I use the left endpoints of my my partition. Questions? Okay, we're almost done. We got 3 more problems to do, and then we'll wrap it up. So I'll continue moving down. So now problem 18 says find the area under this curve from x equals 0 to x equals 2. So long story short, you can use, after you set up a definite integral to compute an area, you can use the fundamental theorem of calculus, the first part, to compute this area. The reason why that I can use the fundamental theorem of calculus to compute this area is because if you look at this function, 2e to the x plus 7, it's always going to be greater than 0. And because it's always greater than 0, I know that I'm above the x-axis. And since I'm above the x-axis, the area is always positive. It's a positive number I'm dealing with. I don't have to worry about any rewrites of the integral or anything here. All I could do is just set up an integral, take its derivative, evaluate it using second fundamental theorem of calculus. So if I set up my integral, the lower limit of integration was 0, the upper limit of integration was 2, then you will have 2e to the x plus 7 dx. So if you ever get trouble setting up this integral, problem 17 gives you a clue. They're not going to be the same functions, by the way. I purposely did this, but if you ever had trouble setting up this integral for problem 18, just look back at problem 17. It gives you an integral. It shows you how to set up one. So that's just a little clue there. Okay. So for problem 18 here, you take your antiderivative. So what is the antiderivative of e to the x? Anybody know?
E to the x.
It's e to the x. So it's 2e to the x plus 7 from x equals 0 to x equals 2. Again, the second fundamental theorem of calculus say you plug in the upper limit of integration first, followed by the lower limits. So it's 2e squared plus 7 minus 2e to the 0 plus 7. And you could have done a little bit, made a little mistake here. I was rushing and I forgot about this. I forgot to take the antiderivative of 7. Yeah, that's right. 7x. So this would have been 7 times 2. And then this would have been 7 times 0.
Wait, so that doesn't get a plus c?
No, definite integrals don't get the plus c. Plus c is only used for arbitrary indefinite integrals. It's an arbitrary number. Here, if you were to add a plus c and then apply the fundamental theorem of calculus, long story short, the plus c's go away because of that minus sign. When you do c minus c, see you later.
Ah, I get it.
There you go. All right. So when you do the evaluations, you get 2e squared, that you would leave alone. 7 times 2 is 14, minus 2e to the 0. That's e to the 0 is 1, so 1 times 2 is 2. 7 times 0 is 0, so you get 2 plus 0, which is 2. So your solution would look like 2e squared plus 12. That's your solution. Any questions?
Oh, so when finding the area of the curve, it's basically that without doing the partition, like n
Yep.
equals.
You just take the antiderivative. So this goes back to something that Shirley was mentioning. What the fundamental theorem of calculus says is that if you have the integral from a to b of little f of x dx, then this is equal to f of b minus f of a, right? Or big F and f of b, or big F of b minus big F of a, where that big F is the antiderivative of little f.
Thank you.
No problem. Yep, is the first part of the fundamental theorem of calculus. There's a second part of the fundamental theorem of calculus, by the way, and the problem that we use to show the second fundamental theorem of calculus makes the second fundamental theorem of calculus very easy to understand. That's problem 19. Ah, crap. I thought I could have been able to slide this down. All right, I'm gonna still slide down. So problem 19, it says evaluate the derivative f prime of x of the function f of x, which is defined here, okay? So if your function is defined by an integral, and then you take its derivative, what the second fundamental theorem of calculus states is that the derivative and integral are inverse of one another, right? It basically undo whatever the other one does. So you get back the original function. However, in this problem, notice that the t here, inside of the integral, you have 3 over the square root of 3 plus t squared. Because we're trying to find f prime of x, you are going to replace the t's with x, okay? So long story short with this one, you say f prime of x is going to equal to 3 over the square root of 3 plus x squared. That's your derivative. Okay, the derivative is exactly what's inside the integrand, except that now you replace the t's, wherever you see a t, that you can think of it as like a dummy variable. You replace that variable, the dummy one, with the good one, the real one, which is x. Now, it says to evaluate this derivative when x is 2, so you get 3 over the square root of 3 plus 2 squared. So what's 3 plus 2 squared? Well, that's 9. So if you take the square root of 9, you're going to get 3. So 3 over 3 is going to be 1. So that would be in your final solution for problem 19, which will leave me with one more problem. But do anybody have any questions before I go to the next problem? Because what I just talked about is huge. Fundamental theory of calculus is huge. But because of time constraint, I've been shortening down my explanations.
Wait, so there you just substitute the upper increment or whatever?
Pretty much. You see, you take the variable x, and you're replacing it, replacing the t's with x, and then you evaluate your derivative at some value.
So in this one, we wouldn't have to take like the antiderivative of that whole quotient.
No, nope,
Okay.
Nope, because the if you look at your function, is defined as an integral. So if you take its derivative, the derivative undo whatever the integral did. Like for example, think back all the way to pre-calc. If I had x plus 5 and I want to undo it, I would have subtracted by 5, right? That same idea is being applied here. Anything else? Any other questions? I appreciate your patience, everyone. Even Raphael. He's the only one, by the way, that's still on campus. I came home to do the
That's a
do the
fact. I'm just
workshop.
waiting for you to finish so I can go to the parking lot.
That's right. That's right. All right, let's do problem 20. We call it a day. Problem 20 says to compute the indefinite integral, x cubed times 12x to the fourth minus 8 times 20, raised to the power of 2022 dx. So here, long story short, you have to use U-substitution for integration. You let U be equal to the inner function of the composite. So the inner function is 12x to the fourth minus 8. You take its antiderivative, you get 48x cubed dx, because the sorry, I didn't say antiderivative, I meant antiderivative. You take its derivative, you get 48x cubed dx. Inside your integral, you have the x cubed dx, but you don't have this 48. So what I'll do is, instead of dividing by 48, it's equivalent to multiplying this whole thing by 1 over 48. So this gives me 1 over 48 du equals x cubed dx. So now I can make a U-substitution. What we're going to get is the integral. The 1 over 48 part can go outside since it's like a constant multiple. Inside of the integral, the 12x to the fourth plus minus 8 is your u. So this will give you u to the power of 2022 du, because x cubed dx gets replaced by that du. Technically speaking, it gets replaced by the 1 over 48 du, but 1 over 48 goes outside. Now you can integrate this. If you do, u to the power of 2022 is u to the power of 2023 divided by 2023 plus the arbitrary constant c. And because you were originally find the indefinite integral in terms of the variable x, you replace the u with what you defined it as for originally. So it's 1 over 48 excuse me, times, in parentheses, this bracket, the power u gets replaced with 12x to the fourth minus 8 raised to the power of 2023 divided by 2023 plus c, plus that arbitrary constant. And that will be it, everyone. That is your final exam review, which we did in 3 hours and approximately 8 minutes. I wish you all the best. If you guys don't have any questions, you guys are free to go. What I'm going to do now is stop the recording because we no longer need it.
Why'd you take the 1 over 48